Greetings everyone. Thank you a lot for joining our webinar today. So my name is Orest and I'm Solutions Engineer here at Starwind. And on today's webinar, we're going to talk about ZFS, and namely, we'll try to see its benefits and the advantages it can bring to your IT infrastructure. Now, this webinar will be a bit technical, so instead of going in all the marketing slang you can typically find over the internet, we'll try to focus on a bit more of the details during this webinar when talking about ZFS. So, what's going to be on today's agenda? We'll briefly take a look at ZFS history, where it came from to us. We'll take a look at the ZFS features, namely pooling and RAID Z levels, data integrity mechanisms, and famous ZFS self-healing. We'll also check CopyOnWrite and Snapshots functionality, as well as the deduplication and compression. At the end, we're also going to see what Starwind has for ZFS. And of course, there will be the Q&A session at the end of the webinar where you will be able to ask your questions. So I believe we are good to jump into this topic. So before we're actually going to talk about the features and benefits, let's just take a few minutes to take a look at the ZFS history. Well, it's no secret, I believe, that ZFS has been originally developed by Sun Microsystems for the Solaris operating system in 2001. The source code was published as open source in 2005 as part of the Open Solaris OS. However, later on, after the Oracle acquired Sun approximately in 2009, it decided to make it actually the closed source. Anyway, during this time, ZFS managed to be ported on Linux as part of the Fuse in 2006. In 2007, Apple started porting ZFS to Mac OS X. In 2008, a port to FreeBSD was released as part of FreeBSD 7.0. And in 2008, the development of a native Linux port started. However, since ZFS is licensed under the Common Development and Distribution License, which is incompatible with the GNU General Public License, it cannot be included in the Linux kernel. So to get around this problem, most Linux distros offer the methods to install ZFS. After that, in 2010, the Illumus project basically forked a recent version of Open Solaris to continue its development as an open source project, including ZFS. And in 2013, the coordination of the open source ZFS moved to another organization, as you know, with OpenZFS, which basically allowed any organization or person that wished to use the open source version of ZFS to collaborate in developing and maintaining a single common version of ZFS. So that's basically the OpenZFS project we know it today. And as of now, there are basically two implementations of ZFS, both quite similar. It's the Oracle's implementations, which is closed source and part of Solaris, and OpenZFS, which is quite widely used to provide ZFS on many Unix-like operating systems. Now let's take the first overview of what ZFS has to show us. So Zettabyte File System, or simply ZFS, is a 128-bit, which is significantly much more than common 64-bit file systems. It allows for storing data with theoretical maximum of 256 quadrillion zettabytes. Well, that's some good handicap for the future scaling, or at least so it's according to the developers. But it's not only the size that ZFS is actually known for, rather the features it provides. And actually, there are a lot of them, and to cover every single one in a detailed way would require a dedicated webinar and a good thought-through article. However, on this webinar, we'll take a look on the most well-known of them. So first, ZFS is not just a file system, but also a volume manager. The obvious benefit of this is that you don't really need other tools to work with your storage. ZFS alone is pretty much enough to create a file system and combine your disks while adding resiliency and managing your ZFS datasets to provide them as a block storage or even NFS or SMB shares. Other features, as mentioned, include duplication, CopyOnWrite, snapshots, and of course, some data integrity. And let's first start with ZFS, basically pulling and RAID Z benefits. Now, apart from just being a file system, ZFS can combine a series of drives into a pool. Moreover, not just to combine, but provide resiliency forming different RAID Z levels, basically replacing the need in a hardware RAID or other software RAID implementation. Now, the basic elements of ZFS are VDEVs or virtual devices, which can be composed by one or more physical hard disks allocated together. The upper level is the Z pool itself, which combines several VDEVs. Often, the pools are associated with the idea of a volume in traditional file system. After the Z pool, you can actually create the additional file systems as datasets or the Z volumes for providing the block storage. Now, talking about the RAID Z, the supported configurations include mirror, which is pretty much analog of RAID 1 with highest resiliency and needs at least 2 disks. Stripe, basically no resiliency and analog to RAID 0. In any case, we are talking about the RAID 0. This, of course, gives maximum speed for read and write operation. But, of course, if one disk goes offline, the ZFS RAID 0, basically Stripes, goes offline with it. RAID Z1, this level resembles the RAID 5 with the minimum of 3 disks needed, where one is used for storing parity information. Apparently, one disk can fail, leaving the data still safe. RAID Z2 and RAID 3 options use 2 and 3 disks for parity correspondingly. RAID 3, for example, can be a good fit for storing mission critical data, while RAID Z2 will be beneficial in terms of performance when comparing RAID Z2 and RAID Z3. Accordingly, RAID Z2 requires at least 4 disks and will use 2 space for the parity, and the RAID Z3 requires at least 5 disks. For RAID 10, it will basically 2 mirror stripes. Now, comparing the RAID Z and comparing the traditional hardware RAID, we have to mention that the rebuild speed for traditional RAID is quite faster. However, traditional RAID has to rebuild both used and free blocks. Rebuild speed on ZFS RAID Z in some cases is slower. However, RAID Z only needs to rebuild blocks that do not hold data. Actually, RAID Z does not rebuild the empty blocks, thus completing rebuilds faster when the pool has significant free space on it. Now, but how does the RAID Z benefit comparing to the traditional hardware RAID? Well, RAID Z with parity is similar to those hardware RAID levels 5 or 6. However, there still is a lot of difference. First, ZFS eliminates the write hole that RAID 5 encounters typically any hardware RAID parity levels. So write hole is a failure of the traditional parity RAID where, for example, parity blocks must always match the corresponding data blocks. However, parity and data blocks are written to different disks. If power fails after the data has been written, but before the parity has been calculated, it will result in data inconsistency. Therefore, some disks will contain old data and some will contain new. In this case, parity won't match the data, causing future issues. This is called the write hole, and it is typically fixed in traditional hardware RAIDs by using battery backup. In ZFS, instead, first of all, the stripe size can be basically set dynamically. Every block is flushed disk in its own stripe size, and every RAID-Z write is a full stripe write. Further, the parity bit is flushed with the stripe simultaneously, basically eliminating the traditional RAID write hole. So in the event of a power failure, you either have the latest flush of data or you don't, but your disks will not be inconsistent. Additionally, you can also set the record size for traditional datasets in ZFS and the volume block size for Z volumes, which are block devices. The defaults are correspondingly 128 kilobytes for the record size and 8 kilobytes respectively for the volume block size. The performance of the RAID-Z levels is basically a separate topic. There are quite different approaches to this on how to determine the perfect stripe width depending on the workloads. However, for best performance on random IOPS as part of the general recommendations, you can use a small number of disks in each RAID-Z group. For example, 3 wide RAID-Z1, 6 wide RAID-Z2, or 9 wide RAID-Z3. This is pretty much because the RAID-Z spreads each logical block across all the devices, which is quite similar to RAID-3, in contrast with other parity levels. Of course, for better performance, you should consider mirroring instead. The other cool feature about ZFS, and basically maybe why it's the most well-known and famous for, is its self-healing. So ZFS is able to detect silent data corruption using checksums and repair them using parity or mirror data, but only in redundant RAID-Z pools. Now, let's take a look at how self-healing works. But before understand that, we need to take a look at the ZFS basically architecture. So whenever the new data is written to ZFS, it creates a checksum for that data. When the data is read, the checksum is verified. If the checksum does not match, then ZFS knows that an error has been detected and will then automatically attempt to correct the error if there is parity or mirror data. ZFS storage pool is basically a tree of blocks. ZFS provides the fault isolation between data and the checksums by storing the checksum of each block in its parent block pointer, not in the block itself. Now, every block in the tree contains the checksums for all its children, so the entire pool is self-validating. Now, the uber block, basically the root of the tree, is a special case here since it has no parent. And the corruptions to the uber blocks are detected by using the checksums inside the uber block itself. If the data and checksum disagree, now ZFS know that the checksum can be trusted because the checksum itself is part of some other block that's one level higher in the tree, and that block has already been validated. This allows ZFS to detect what we call the silent data corruption. So if the data that is read does not match the expected checksum, ZFS will try to recover the data and provide good data to the application and repair damaged copy once again from the available redundancy, like mirrors or parity. So as you probably can see, the blocks of ZFS storage pool basically form a Merkle tree, in which each block validates all of its children. Additionally, Merkle trees provide the cryptographically strong authentication for any component of the tree and for the tree as a whole. Now, ZFS employs 256-bit checksums for every block and offers checksum functions ranging from fast Fletcher 4 to the slower but more secure SHA 256. And the default currently is Fletcher 4. Now, so how it actually happens with the RAID-Z? So suppose the application needs some data blocks, and in those blocks, one of them is corrupted. As we know, ZFS is aware of this by checking the checksum of the block, as already mentioned. If a checksum does not match on a block, it will look at other disk in the mirror, for example, to see if a good block can be found. If it is found, the good block is passed to the application, and then ZFS will fix the bad block in the mirror so that it also passes the checksum. As a result, the application will get the good data, and your pool will always be in a good, clean, and most importantly, consistent state. Now, a part of the ZFS benefits covering the RAID Z levels, there is also some inconvenience, especially when it comes to extending ZFS RAID Z pools. Now, in fact, it appears that ZFS RAID Z is something that should be well planned, taking into account the future grounds needs, and here is why. You can grow your RAID Z pool by adding a new VDEV. You need to be aware though that each VDEV in a ZFS pool will basically play a role of a single fault domain. So if you add a single disk as a VDEV to your mirrored VDEV, it will become a single point of failure. Therefore, it is highly recommended to add VDEVs of same resiliency type and also recommended of the same size. Alternatively, the other way around, you can replace the disks one by one with larger size disks. The total size will increase only once you replace all of the disks in that pool. Now, once the RAID Z self-healing functions are pretty much understandable using the parity and mirroring functions, what about ZFS resiliency without the RAID Z? In fact, it still has some options in this case. Now, ZFS is able to recover from single metadata block corruptions by using block replicas. Actually, ZFS keeps 3 data blocks for pool-wide metadata and 2 for file system metadata. So basically, what these data blocks are, each block pointer, as we discussed earlier, contains pointers to up to 3 copies, which are basically these data blocks of the block being referenced to. But once again, ZFS does not recover from data block corruptions unless there is parity or mirror data. Although, of course, not recovering from the corrupted data, you still can see and check your ZFS health by running the scrub to additionally cover the data that might not be read during typical workload. So scrub is pretty much similar technique to ECC REM, where if an error resides in the ECC DIM, you can find another register that contains the good data and use it to fix the bad register. While ZFS is performing a scrub on your pool, it is checking every block in the storage pool against its known checksum. Every block from top to bottom is checksummed using the appropriate algorithm. By default, it's Fletcher 4, as we discussed. Now, scrubbing of ZFS storage pool is not something that happens automatically. Instead, you need to start it manually. And it's highly recommended that you do it on a regularly scheduled interval. The pretty much recommended frequency varies, but depending on the quality of your underlying storage, for the SAS disks, for example, once per month should be pretty much sufficient. So once again, with all this being said, we should still keep in mind that ZFS on its own does not protect you against data corruption without resiliency. Now, another mechanism on the list that allows us protecting the data consistency on our ZFS pools is the CopyOnWrite. So CopyOnWrite is a data storage technique in which ZFS first makes a copy of the data block that is going to be modified. rather than modifying the data block directly. Then the pointers are updated to look at the new block location instead of the old one. It also frees up the old block so it can be available to the application. Thus, you don't use more disk space than if you were to modify the original block. The CopyOnWrite model also opens up new features for our data that were previously either impossible or difficult to implement. Also, in the event of a short write, for example, when a system crash or a power loss in the middle of writing a file, the entire original content of the file is still available and the incomplete write is discarded. This also means that ZFS does not require the file check after the unexpected shutdown. Now, the biggest feature of CopyOnWrite is taking snapshots of your data. Because we made the copy of the block elsewhere on the file system, the old block still remains, even though it's been marked as free by the file system. So with CopyOnWrite, the file system is working its way slowly to the end of the disk. It may take a long time actually before the old freed up blocks are rewritten to. And if a snapshot is taken, it's treated as a first-class file system. However, the CopyOnWrite also causes the negative effect, which is the fragmentation of the underlying data, which may become a real issue with busy applications like databases. So this is something that should always be taken into account. Now, talking more about the snapshots. Well, snapshots in ZFS are similar to snapshots with Linux LVM. A snapshot, as mentioned, is a first-class and read-only file system. It is basically a mirrored copy of the state of the file system at the time the snapshot was taken. Now you can take up to 2 in the 64-degree snapshots in your pool, which is the theoretical maximum. ZFS snapshots are persistent across reboots and they don't require any additional backing store. They use the same storage pool as the rest of your data. A ZFS snapshot is a copy of the Merkle tree in that state, except we make sure that the snapshot of the Merkle tree is never modified. So how basically does it work? After taking a snapshot of a dataset or a recursive snapshot of a parent dataset that will include all child datasets, new data is written to new blocks, but the old blocks are not reclaimed as free space. The snapshot basically contains the original version of the file system, and the live file system contains any changes made since the snapshot was taken. So no additional space is used. As new data is written to the live file system, new blocks are allocated to store this data. The apparent size of the snapshot will grow as the blocks are no longer used in the live file system, but only in the snapshot. The snapshots can be mounted read-only to allow for the recovery of previous version of files. It is also possible to roll back a live file system to a specific snapshot, undoing any changes that took place after the snapshot was taken. Also, the ZFS snapshot is a basis of ZFS replication. Basically, what this means that ZFS provides the built-in serialization feature that can send and stream representation of data. It is also possible not only to store the data or another pool connected to the local system, but also to send it over a network to another system. Basically, this will resemble the form of asynchronous replication. And continuing our topic instead of ZFS snapshots, let's talk about the techniques ZFS has for storage savings. So the first one on the list is ZFS compression. Now, ZFS compression is transparent if you enable it. So what this means is that every file you store in your pool can be compressed. From application point of view, the file does not appear to be compressed, but appears to be stored uncompressed. What this means is that if you run the file command on your plain text configuration file, it will report it just as such. Instead, under the hood, underneath the file layer, the ZFS will be compressing or decompressing the data on disk on the fly. Also, compression is enabled or disabled per dataset or per volume. The supported compression algorithms previously were LZJB, LZ4, ZLA, and gzip, but since the LZ4 has been introduced to ZFS on Linux, it is now the preferred way to do compression with ZFS. Of course, compression efficiency can vary on the disk space saved. If the dataset is storing mostly uncompressed data such as plain text, log files, or configuration files, the compression ratios can be quite huge. If the dataset is storing mostly compressed images and video, then you won't see much, if anything, in the way of disk savings. With that said, compression is disabled by default, and enabling does not seem to yield any significant performance impact. So even if you're storing largely compressed data, for the data files that are not compressed, you can get those compression savings without significantly impacting the performance of the storage server. Also, what we should note that enabling compression on a dataset does not work backwards. It will only apply to newly committed or modified data. Any previous data in the dataset will still remain uncompressed. And of course, the other technique that ZFS provides us with for ensuring space savings is the deduplication. Now, ZFS uses the block deduplication only. Block deduplication shares all the same blocks in a file minus the blocks that are different. This allows storing only the unique blocks on disk and reference the shared blocks in RAM. It's more efficient than byte deduplication and more flexible than file deduplication. However, it has a drawback. It requires a great deal of memory to keep track of which blocks are shared and which are not. So, what makes it possible to detect duplicate blocks of data as they are written is checksums. So with deduplication, the reference count of an existing identical blocks is increased, saving storage space. To detect duplicate blocks, a deduplication table, or simply DDT, is created and kept in memory. The table contains a list of unique checksums, the location of those blocks, and a reference count. When new data is written, the checksum is calculated and compared to the list. If a match is found, the existing block is used. Also, the SHA-256 checksum algorithm is used with the duplication to provide a secure and cryptographic hash. Now, because DDT must store the hash of each unique block, it consumes quite a large amount of memory. There is basically a general rule of thumb, which is approximately 5 or 6 GB of RAM per 1 terabyte of the duplicated data. In situations where it is not practical to have enough or such huge amounts of RAM to keep the entire DDT in memory, performance will suffer greatly as DDT must be read from the disk before each new block is written. Instead of that, the duplication can use the L2 arc to store the DDT. The L2 arc is basically the SSD caching, providing a middle ground between the fast system memory and slower disk. Considering using compression instead might be even more beneficial without taking that much off your RAM for the duplication. Also, just as with compression, only data committed to the dataset will be checked for duplicate blocks. It is not the backward compatible on the previously committed data. It is only applied to the new or modified data. Further, the deduplicated data is not flushed to disk as an atomic transaction. Instead, the blocks are written to disk serially, one block at a time. Thus, this does open a chance for corruption in the event of a power failure before the blocks have been written. And before we gonna jump to the StarWind and ZFS implementation, let's take a look at some final ZFS recommendation. So typically, the typical recommendation for ZFS to run is 5+ GB of RAM for ensuring optimal performance. Of course, you can use it with less of RAM or your system, but the performance in that case might be degraded. Also, ZFS is not recommended or hardware rated for the following reasons. So first of all, it does not protect you against the write hole. So for example, if a hardware RAID controller's write cache is used, an additional failure point is introduced that can be only partially mitigated by adding complexity from adding flash to save data in power loss events. However, the data can still be lost if the battery fails when it is required to survive a power loss, or there is no flash and power is not restored in a timely manner. Also, hardware RAID will limit ZFS to perform self-healing functions on checksum failures. When ZFS does RAID-Z or mirroring, a checksum failure on one disk can be corrected by treating the disk containing the sector as bad for the purpose of reconstructing the original information. However, this cannot be done when a RAID controller handles the redundancy. And further, using ZFS with the disks directly will allow it to obtain the sector size information of the ZFS, which we know as the dynamic strapping. In case of the hardware RAID does all the writes, there will be no real benefit from the ZFS feature. So, as the final recommendation, the HBA should be used instead of a traditional RAID controller. Also, talking about the cases when ZFS should be implemented. Well, due to its resiliency, self-healing, CopyOnWrite, additional copies of the pool-wide metadata and file system metadata, ZFS actually becomes a perfect fit for archival backup storage. Also, it becomes a good pick for large storage amount such as NAS, as you probably know with the FreeBSD projects. Additionally, yes, ZFS has been created with the virtualization in mind as part of Solaris, so it also can be used for production and virtualization workloads. However, from the technical perspective and taking into account the CFS feature, it's mostly the best case for the archival and backup storage needs. Now, talking about the StarWind and ZFS. StarWind is adding ZFS in its StarWind Virtual SAN for vSphere product. So just to show you what I actually mean, on my demo stand, we pretty much have a typical StarWind cluster on the ESXi. We have two ESXi nodes. StarWind Virtual SAN is installed on each of those as the Linux-based virtual machine. And since it's Linux-based, it, of course, allows us getting the benefits of the ZFS, and ZFS already comes implemented with the OVF template. So we not need to additionally install the modules of ZFS kernels. Now, for example, for my testing lab and to show you how currently ZFS is implemented, let's take a look on what we actually have here. Now, I have added just a couple of disks which are virtualized. This is basically the VMware virtual disks. So SDB1 and SDC1 are basically just the simple partitions, as we can see from our storage tab. The same goes for the second virtual machine. Now, since ZFS already comes implemented in the StarWind Virtual SAN for vSphere, Let's actually check and create the Z pool and try putting the StarWind HA device on top of it. So since I've added just 2 disks on each virtual machine, we're just gonna make a simple mirror pool. And since these are not the real physical disks, I'm just gonna add them using the basically the partition UID we have here. And for the second guy, okay. So we have our Z pool on the first virtual machine. And now let's just do the same on our partner virtual machine. Okay, good. Now, since StarWind requires the block storage beneath it, we're gonna create the volume, the Z volume. So it's just gonna be a tiny size. And just name it disk. Oop, sorry. Okay, now this should go. Well, nope. Okay, finally. Now, and let's repeat the same. Create volume 1 GB and on our StarWind ZFS pool. Okay, good. Now, currently, I should note that ZFS has not been yet officially released in the StarWind build. It is already present and it will be officially supported in the upcoming build. So currently, we can see our new ZFS device. However, Starwind yet communicates with the storage over the XFS file system. In the future releases, we're gonna make it talk directly to the ZFS volume. However, for now, we are still requiring the final XFS file system. So I'm just gonna create the XFS on top and just mount it. And the same on the other virtual machine. And the mount point. Now, if we go to the Starwind Management Console, we can see our two Starwind VMs connected, and one device is already created there. There's just some other testing device. So let's actually create the Starwind HA image on top of our ZFS disk. I'm gonna just name it ZFS, 1 GB of size, just for demonstration. And here is our new disk 1. And apparently, I believe we will take the less disk space for this demo. Since unfortunately I cannot just play with the storage amounts I would like to, so I have to use what I have. Now let's replicate the device. We're going to add the synchronous two-way replica to our partner node. And let me just remind myself about the partner IP address, 84. Yep, the last one in the list. Heartbeat, create a new partner device on the partner storage, selecting our mount point and our disk. We are also setting the Starwind replication settings for the networks, heartbeat synchronization and management as an additional heartbeat channel, and creating replica and synchronizing the storage between both sides. So the synchronization process is going, just a tiny device, and finished. So as you can see, we right now have the Starwind HA device, which in case of Starwind Virtual SAN for vSphere can be further presented to our ESXi nodes as the HA VMFS data store. And we can see our new Starwind iSCSI disks, 500 megabytes. Dynamic passes includes passes from both nodes. And the same goes for our partner nodes. I just rescan the adapter and our new disk appears right there. We can further create the HA VMFS data stores on top. Now, this was just a brief Starwind demonstration. I'm not covering all the other features ZFS can offer since, as I said, it's still not yet officially released, and we are working on also adding the snapshots and the duplications features for the Starwind HA storage, which will be situated on top. However, this will give you the overall idea, I hope, of how Starwind implements ZFS inside of the Starwind Virtual SAN for vSphere. And now I believe it is the time for your questions. So in case you have any, please let me know. If you have any questions. And so the question, ZFS shouldn't be used with hardware RAID controller, and that is add CPU or some other overhead for general I/O, not considering the duplication now. Well, first of all, so hardware RAID controller is not that of the CPU intensivity. It's basically because of eliminating the beneficial features of the ZFS. It can be used. However, the ZFS will not provide the checksums, basically will not protect you against the write hole, and will not basically provide you for the reconstruction in case of the silent data corruption, which should be relied on the hardware RAID functionality. Also, I can see another question. How does ZFS compare to ReFS plus storage spaces? Well, I believe this was asked till we got to the snapshots. So of course, the snapshot is not like the unique systems, but ReFS plus storage spaces is a bit different implementations. Also, I can see the note that DFS is not copy on write, it's the redirect on write. Well, in fact, the Oracle documentation mentioned it as the redirect on write. However, making it the fact that ZFS does not overwrite the block, makes a copy and then updates the copy instead. So it's pretty much, I believe, something that is still in terms of the definitions. Also regarding the record, yes, it will be available during 2 weeks, I believe, on the website, and you will get the email notifications with the recording. Now also I can see the question, how is current implementation of ZFS perform after 75% capacity? Well, typically as the capacity, as the utilization of the storage grows, the ZFS keeps dropping down the performance. Actually, not just keeping down the performance system, it's mainly because of the rebuild speed. Also, the rebuild speed, basically the rebuild slowness increases with the number of disks in the VDEV participating. The release date for the next build with ZFS is planned approximately a couple of weeks. Well, taking into account all the circumstances, it might still be delayed a bit. So we should basically point to a month instead. Also question, how are you passing disk from ESXi storage to VM to create the Z pool as mirror? Well, in my case, just in my virtual lab, it was still the VMDK. In other side, you can just make it as RDM, raw device mapping, directly to the virtual machine. Can hot swap be used with ZFS? Yes, it can be used, especially when you're planning to replace the disks. It is really beneficial since you will not need to stop the system and then remove the drives, insert them and replace. Can I use the disks of different sizes? Well, Z pool will always be determined by the size of the lower device. So pretty much, yes, you can, but still it will not gain any significant difference. You can make another VDEV with a smaller size, but it is still recommended for performance reasons to keep them on the same capacity size as just well as on the same resiliency type. Other storage devices already using ZFS as backup archive targets. Unfortunately, not aware of this yet. Starwind plan to support for ReFS pools for Hyper-V clusters. Well, yes, Starwind pretty much does already support the ReFS pools for the Hyper-V. Okay, so I believe we'll be rounding our webinar up. In case I missed any questions, they will be answered at the beginning of the upcoming webinar. Also, the record will be available in a couple of weeks on our website, and the email newsletter will be, of course, sent. So thank you everyone once again for joining. It was a pleasure holding the webinar for you today, and wish you good luck and everything best. Thank you.